welcome back to the London Futurist podcast. In the future, energy will be too cheap to meter. That used to be a common vision of the future, abundant, clean energy. If not exactly free, then much cheaper than today's energy. But a funny thing happened en route to that future of energy abundance. High energy costs are still with us in 2023 and are part of what's called the cost of living crisis. Moreover, although there's some adoption of green, non-polluting energy, there seems to be as much carbon-based energy used as ever. Regular listeners to this show will know, however, that one of our themes is that forecasts of the future often go wrong, not so much in their content, but in their timing. New technology and the associated products and services can take longer than expected to mature, but once a transition does start, it can accelerate. And that's a possible scenario for the area of technology we're going to be discussing today, namely space-based solar power. Joining us to discuss the prospects for satellites in space gathering significant amounts of energy from the sun and then beaming it wirelessly to receive us on the ground is John Bucknell, the CEO of the marvelously named company Virtus Solis. John has been with Virtus Solis as CEO and founder since 2018. His career previously involved leading positions at Chrysler, SpaceX, General Motors, and the 3D printing company Divergent. John, thank you for joining us today.
Thank you and good morning.
Thanks for joining us, John. I'm really looking forward to this. It's a subject I don't know much about and it sounds properly science fiction, but I'm sure you're going to tell us why it's not.
I will.
Well, let's just start with the name of your company, John, Virtus Solis. What does that mean?
So as a solar power energy company, the choices that don't use solar and power in the name are few and far in between because this technology has been around for a long time. When naming the company, I had to jump to another language. Virtus is the root of virtue. It's Latin, of course, and then Solis is the sun. So really it is power of the sun, and my website is virtussolis.space, so space solar power is the actual name of the business, and it is self-explanatory if you have your high school Latin still with you.
My high school Latin has deteriorated in the preceding decades, sadly. Talking about preceding decades, as Callum mentioned, there is an account that space-based solar power is literally science fiction because it featured in a story by Isaac Asimov as long ago as 1941, which is 82 years ago. Are we getting any closer?
Indeed we are, but I'm going to add a little bit of color there. Space-based solar power is actually older yet than that. A Russian school teacher by the name of Konstantin Tyarsky, a prolific inventor and also the inventor of the rocket equation, which was written in 1897, which preceded actual rockets by quite a bit, wrote down space-based solar power in 1921. Isaac Asimov actually knew of the paper that Tyarsky wrote and included it in that book called Reason. And then later, Dr. Peter Glauser proposed the first engineering study in 1968. So as concepts, space-based solar power has been around longer than I have, but a number of organizations, including NASA, JAXA, the Chinese, the UK, many organizations have all pursued this technology over the years, but the underlying infrastructure, the technology feeding it, weren't quite ready yet. The most recent studies that you might have heard of, NASA did a large study in the late 70s, and then most recently 2010, I think was the last pass NASA made at it. But there's been a lot of activity recently on this topic between ESA and the UK Space Energy Initiative and others. So we're making progress closer to making this reality today.
I'm sure that when most people first hear of the idea of beaming solar energy to the Earth from satellites, the two things that will pop up in their heads is firstly, doesn't it fry everything in the way? How do you beam the energy safely to Earth? And secondly, isn't it fabulously expensive to put solar cells onto satellites in space or onto asteroids or on the moon?
Let's address the power beaming first. The main thing to consider about frying and the danger is intensity. Intensity is a measure of how many watts per unit area you're dealing with. Sunlight, as you might know, is 1 kilowatt per square meter. Most of us can go outside on a sunny day and tolerate that amount of heat that enters your body through your skin. Most proposals we're dealing with with microwave wireless power transfer are fractions of sunlight. They're just photons or different wavelengths than the sunlight that you might experience outside, but systems that are low intensity are by nature not dangerous. As an alternative, lasers by their very nature are high intensity, so if you're transferring power wirelessly via lasers, those are more of a challenge. But we've chosen microwaves for a number of reasons, primarily because they're safe and not weaponizable is a very important topic, but also because they're longer wavelength, they don't interact with the atmosphere and the water vapor, which is clouds, and therefore they are useful for radar because those electromagnetic waves do penetrate clouds and weather and useful for aircraft. We're using a frequency at 10 gigahertz that is actually the same as weather radar, so you're able to pass through atmosphere and weather with low loss, almost none. We actually only book about 3% for the last couple of kilometers from our 35,000 kilometer altitude. So those systems are quite safe. The other bit, which is the unit economics and how to generate energy at a cost that people can afford. The reasons why it was so expensive in the past, in fact, NASA, who did the first large study in the late 70s, produced something called the NASA 1979 reference design, which at the time they asked for $500 billion US of today's money and said the first system would be available in 2006. $500 billion is a lot of capital, but what it required was mines on the moon to get raw materials, factories in space to turn those raw materials into finished goods, habitats in orbit to house the astronauts who put it all together, and then last but not least, needed the space shuttle and its derivatives to reach $50 a kilo to low Earth orbit, which they never reached 3 orders of magnitude from. So the underlying infrastructure didn't exist yet. That was 40-some years ago, but the assumptions that were true back then are not true anymore. The biggest one is commercial space launch. You can buy a ride today on a SpaceX Falcon Heavy at about $70 to $100 a kilo to low Earth orbit. That assumes no reuses. In fact, just like commercial aircraft, rocket reuses are on the rise. SpaceX, a couple of days ago, landed a first stage of their Falcon 9 17 times. That is quite a bit of progress from ages ago when most systems were barely one use. That's changed primarily, and then the other big things are Moore's Law and semiconductor manufacturers. Power electronics and all those elements you need to make a power system work have progressed many orders of magnitude in reduction in cost and in mass, and then of late, automated manufacture and assembly through robotics also has made large strides. You can buy a robot to unload your truck at a warehouse for less than the annual cost of paying a worker. And that system works 24 hours a day, 365 days a year. All those trends have been going in the right direction.
Can I just follow up on getting the power to the Earth? If you're sending it at such low intensity, how do you send enough power to be useful?
There are a couple things to consider. Sunlight that reaches the ground for terrestrial solar, generally only about 20% of it is converted. Photovoltaic cells for large-scale terrestrial utility-scale solar, the most cost-efficient systems are about 20%, 19 to 21 is the general range. Some solar cells available today are in the high 40s, 46, 47% is about world record. But keeping in mind that there is such a thing as weather and day and night. So even though the photovoltaic cells are able to generate a relatively small amount of energy for the incident sunlight, at best, they're only able to generate energy about half the time. And at worst, it's about 1 to 3%. If you look at the historical record in Germany, which has been trying to convert to renewables for about 20 years, we find that those of us that live in northern latitudes have almost no sun in January and February in the wintertime. So the key element that you have to understand is not just that the intensity is low, and we'll talk about that in a moment, but capacity factor is very important. In space, it's always sunny. There's no clouds, there's no weather, there's no night. So you can get close to 100% capacity factors on your generation, which is the satellites in orbit, and then transferring it to the ground. If you're high enough, you can move that energy to the ground most of the time, if not all the time. So you already have a 3 to 5x improvement in the amount of energy that's generated. The other thing you have to keep in mind is that radio waves, microwaves are electromagnetic, just like sunlight, but photovoltaics is a different physics. Photovoltaics knock an electron out of position and then generate a voltage and current that way, whereas electromagnetics are directly converting current to a RF spectrum. And so those systems are very efficient. You can convert DC current to microwaves at above 90% efficiency, and similarly, you can convert radio waves back into electricity very efficiently as well, above 90%. In fact, the theoretical highest is 100%. No one's demonstrated that high, but 96, 97, 98% have been demonstrated.
One more question about the physics. How do you stop the beams from spreading out? If they're not laser-like, won't they go off with some R-squared decrease?
It's actually R to the fourth, but let's talk about that a little bit. A single antenna, which most of us think of for radio antennas, is like a bonfire. The radiation goes in all directions. But we are using phased array antennas, which have high directivity. So high directivity means that the energy is going in one direction. In fact, phased array antennas, most directional antennas have a reflector behind it. So if you are used to a candle that you're using to find your way around in the late 1800s, you generally have a reflector behind it. So some of the photons, or most of the photons that are going one direction, are reflecting the other. Phased array antennas, if you have enough of them, and we're talking about systems with billions of antennas, they act more like a surface emitter, which is exactly like a laser. We have already demonstrated systems that have beam divergence of thousandths of a degree. So it effectively is like a laser. It is a coherent beam like a laser, and it is also electronically steerable, unlike a laser, such that you can track ground targets very, very accurately. So all these things come out of the development of radars, which have been around for 70 years.
We'll be right back after a quick break.
The People in Performance podcast offers insights into the strategic competencies, behaviors, and results needed to increase the performance of employees and leaders. The show looks at all areas of the world of work, including attraction and recruitment, onboarding, training, and succession planning. Tune in to get a better handle on the stages of workforce planning you need to master in order to guarantee long-term success in a rapidly changing world of work. New episodes drop each week. Check out the latest People in Performance episodes on your podcast platform of choice. Follow us on socials and read the latest articles at pppod.com.
So you're talking about some encouraging trends. You're pointing out that Moore's law isn't just about making computation go faster, it's about improving photovoltaics, improving the ability for these systems to pick up the energy from the sun and do useful things with it.
But Moore's law is more important for the power electronic. Most of us have many radio antennas in your cell phones, for example. There's generally about 15 to 20 radio antennas. The underlying semiconductor manufacturing techniques that improve the processing performance also manage the power. If you might have had a cell phone for the last 20 years, you know that the duration that these systems last based on the amount of computation power gets better and better, and that's mostly because Moore's law has allowed finer features which lower power consumption and improve the performance of these systems. And that's really the trend that makes power electronics for radio frequency use much, much better.
But how fast are these trends going to help? Are we looking ahead to space-based solar power scaling up quickly enough to make a significant difference to plans to reach carbon net zero by 2050, say?
As a startup founder, my investors certainly hope so. If I'm not able to deliver in the next 5 to 7 years, then they wouldn't be able to invest in me. I would argue that the technological trends have already arrived where they need to be. The last big one that needed to be solved was wireless power transfer. And if you were at the CogX Festival or the Wired Energy Tech Summit this last week, I brought a technology demonstrator showing, hey, look, you can do a wireless power transfer at significant distances already. And it's a scale-enabled technology. The bigger you make it, the better it works. We would argue that all those trends have already arrived. In fact, the advent of the SpaceX Falcon Heavy in 2018 has made the business cases possible to close at costs are competitive with existing energy. So we believe they're already here, and it's just we need to develop commercial products around those underlying technologies.
How quickly can this technology be adopted and deployed widely? I suppose the key thing is, how is the energy received from the beam from space and then converted to a useful purpose, heating a house or something? What's the mechanism in between?
Let's talk about that mechanism first. So as I said earlier, RF radio frequency waves are easy to convert from current to radio waves and back again. We have a receiving antenna. Any transmit antenna can be a receive antenna. Our receiving antenna has a rectifying circuit on it, so it takes those oscillating waves and turns them back into direct current. In fact, they look a lot like solar panels, in the installation on the ground. Any antenna can work, but you want to make the system most efficient. Ours looks like a patch antenna, so it's a flat plane that looks like a circuit board with small amounts of electronics on it. So we build receiving panels that look like solar panels. We install them like solar farms. Because the energy is not ubiquitous like terrestrial utility scale solar, you want to collect all the radio waves that are incident. So you're going to put a ground station on the ground that receives energy and connects it to the local grid or the end user, whatever the end case may be, so that you can maximize the utilization of the asset in orbit and make the best unit economics. So it's going to look like a solar farm that's parked near the end users, and then you'll have a local distribution grid that delivers it to your home. So that's the way we envision it working. In fact, it's small enough that you can fit it on the ground site of existing power stations. So we're about 2 kilometers in diameter for a 1.5 gigawatt capacity receiving station. That's very much in line with a nuclear power plant. Most markets don't need more than that, but some do. So these systems are very much drop-in replacements for existing generation.
So you'd have a receiving station for a large city block or for a city, not for a house, is that right?
Yeah, for sure. A gigawatt and a half is about 150,000 people. All their energy needs, that's about 10 kilowatts continuously for each of them. So that's very energy rich. And that's what we experience in North America across all our energy uses. If only 15% of your energy use is electricity today, that's 1 million people. So that's a decent sized city.
And how much would one of those cost? I mean, obviously, initially they're going to be expensive, but say after 5 years of deployment, what's one of those receiving stations going to cost?
We would argue the unit economics are 2.5 to 3 times what a utility scale solar farm is. And that would make price points for that many megawatts is in the billions, but very competitive with existing commercial power plants. Almost all the costs of these solar farms, whether they're space-based or terrestrially based, you're paying for the manufacture of the components. The amortization period, generally for terrestrial solar farms, about 30 years. We're only seeing 20. But because you're generating so much more energy per amount of capital invested, your return is actually far better. These systems can bring energy costs down below $30 a megawatt hour, 3 cents a kilowatt hour. And that's during the amortization period. After that, it's basically free. It's under $1 a megawatt hour, which too cheap to meter is almost the word to use.
And aren't governments doing enough to assist this? I know that the UK government has announced that this is one of their initiatives in general, space-based power that they want to get behind. Is it just lip service, or are they doing something significant?
They're doing something. Actually, Vertisolis is already operating under a grant from the initial tranche of money that was allocated. But just like many things, the governments need to be assured that this is the right answer. So as part of the Net Zero Initiative in the UK, they're investing in offshore wind, onshore wind, utility-scale solar, fission, and space-based solar power. They're investigating all of those. Space-based solar power is the only one that doesn't have a use case that's already in existence that you can study and figure out the economics. I would say that they could do better. A lot of that money that has been allocated for the Net Zero Initiative has not yet been made available to interested parties. There's a lot of arguing, of course, among the government agencies about how to spend that money. But ESA, the European Space Agency, has also picked it up. They have actually put more capital into it as far as an allocation under their Solaris program. They've got a 5-year plan to study it, make a recommendation on how to allocate the funding in the EU. The U.S. has yet not got to the point that the government supports it. The interesting thing is the current chief technologist at NASA, his name is A.C. Charania. He's been on the job since the start of this year. He was actually part of the most recent study that NASA did in 2010. We're expecting them to have a position paper later this year, but NASA's busy. They have a lot of things that they're chasing, and they're more of a science exploration type agency as opposed to a commercial power development agency. And that's really, at least in the U.S., has been the challenge, is that the Department of Energy is responsible for energy, and NASA is responsible for space, and when you straddle both, neither take ownership. I would argue that you need to have a proof point. You need to have a demonstration that it works, and then funding will flow in. And that's been the case for almost all technologies, with the exception of fusion, which has never worked, and it still continues to get billions of dollars per year of investment.
Previously in your career, you worked at SpaceX, which is Musk's space exploration vehicle. And this sounds like a project that would excite him. Is he pursuing this at all?
No, Elon does not believe this is a feasible topic, mostly because of the efficiencies involved. Certainly, they are more in the space transportation and telecommunications realm these days. Starlink is probably going to be their primary source of revenue here in the near future. But as a space launch business, I believe they'll take anyone's money if you have a big enough check to pay for their launch services.
So what are these governments actually studying? You said they need a proof of concept, and you say you've already got a proof of concept, but I guess that's only beaming power from one side of a stage to another. Are you any time soon going to beam power from space to the ground?
Yep. In fact, there have been a couple of demonstrations. JAXA did a power beaming exercise from one satellite to another over a decade ago. Caltech, which is a research institution here in the U.S., has a demonstration mission that launched in January and has been operational since late May, early June. They did a wireless power transfer in space and also was detectable on the ground. But nobody's done large scale yet. We plan to have a pilot plant in orbit in about 3 years and first commercial deployment before the end of the decade. This is deep tech. This takes a lot of capital to build and test, but that timescale is relatively near term. Having a commercial power plant operational that the unit economics of the customer are evident is usually the proof point that you need to see a large amount of capital flowing in for scaling.
And what's possibly going to go wrong between now and the next 3 or 4 years when you hope to have this system in place? What are the things that might keep you up at night worrying about lack of support or lack of technology or whatever?
We do not depend on anyone else other than investors to support us, so our model is very straightforward. The underlying technologies have been in evidence since the first commercial satellite in the early 70s. The solar panels in space have been up there. There are several satellites that are up there that are over 30 years old, some approaching 40 or more. The underlying electronics, all those have gotten better. In fact, most satellites that launch today have no space heritage. They're built and tested on the ground, and they put them up there, and they work fine. But obviously there are things that you don't know. Most of the important things to our customers are whether or not we can reach the unit economics that we describe. And as an engineer and co-founder, my co-founders and I both have 30 years experience in industry. Personally, I've been in charge of 8 production programs. We see this more as an engineering challenge and supply chain challenge, frankly. Those are the bigger things that we worry about because the scale of what we're planning to do is large. So if I say I want to go and find 200 megawatts, which is the first commercial system size we're planning, of space-rated solar cells, no one has that. We would have to do what SpaceX is doing with Starlink and use terrestrial utility-scale solar cells, which are not space-rated. They deteriorate quite rapidly, but the lifetime of their system is about 5 years, so they can tolerate that. Whereas ours plan to be up there 20, 30, 40, even as high as 80 years. So getting the supply chain spun up is probably the biggest challenge for us to confirm that it's there. Our system is capital intensive compared to other startups, but not compared to other space startups, and much more capital light than a lot of research and development programs that are fighting physics. And I'll use fusion as the example again.
You say that your installations in space would last for 30 to maybe 80 years. What deteriorates them? Is it strikes by particles and very small meteorites, or does the equipment just decompose slightly on its own?
Good question. I would argue that the reason that the satellites that are in orbit today run out of life is they run out of propellant for station keeping and orbit keeping. In fact, there's a whole industry that's spun up around servicing those satellites and providing more propellant. Knowing that we intend to have a very long life, we've designed around that. Our systems are all solid-state electronics. There's no fluids to lose. There's nothing like that. It's a relatively benign environment. The radiation itself, you can design for it so that you don't have bit flips in your calculation electronics. And the solar cells themselves, generally the spacecraft you'll see have bare solar cells. They're exposed to the radiation that's in the space environment. However, if you go heavier and put radiation hardening, which is generally some amount of mass in front of your components, the radiation that reaches them is much lower. So we intend to do what we do with terrestrial solar cells, is put a layer of glass between the solar cells and the sun. Silicon-based solar cells degrade with radiation if they're bare. There are solutions today. There are several companies that are building silicon-based solar cells that are space-rated that have much lower deterioration, and there's space-rated solar cells that don't deteriorate effectively. They lose a couple of percentage points over 20 years. So knowing all the things we know about the space environment, since we've been up there for 70 years, is that you can design systems that aren't ultra lightweight. Generally, the problem with space launch is that it's been so expensive, you have to have extremely well-engineered, very lightweight solutions. Whereas as launch costs come down, you can put that extra margin in there to make your system last longer. I would argue that the space debris challenge is more of a problem for low Earth orbit systems below 2,000 kilometers altitude.
Your systems aren't low Earth orbit? Do they go much higher up?
Much, much higher orbit. Let me finish the debris discussion. If you're up in those higher orbits, there's very little chance you're going to run into debris. There's tens of thousands of objects that are below the 2,000 kilometer altitude. But above that, there's very little. Geostationary is quite quiet in the debris regime. Most of the satellites that are 40 years old or older are in geostationary. Coming back to where you would put these satellites in orbit, generally your ground stations are fixed. They're large installations, they're not moving. So you want an orbit path that's ground synchronous. Ground synchronous means that you're overhead with a satellite at the same time as the Earth rotating. So Earth rotates a little under 24 hours per day. A sidereal day is 24 hours, 56 minutes, which is the actual time it takes for one rotation. And it's interesting that over the course of a year, the position on the ground pretty much stays the same. And this is where the 365 and a quarter days comes from. If you want a satellite overhead, you're going to take an orbit period. It's going to be the same as a sidereal day if you want to be ground synchronous, and divide that by an integer. So geosynchronous and geostationary are 24 hours divided by 1. There are 12-hour orbits that are geosynchronous divided by 2 and 8, 6, 4, 3-hour orbits as well. But as you go shorter orbit duration, the lower the altitude is, and the more time those satellites spend in Earth's shadow and out of line of sight of the ground station. So really the only two solutions are geosynchronous or geostationary, which are slightly different orbits. One is in the plane of the ecliptic, which is the plane that goes through the Earth's orbit around the sun. The other one goes to the equatorial plane around the Earth, which has a 23-degree tilt. We're using Molniya, which is a Russian orbit originally, which is a 12-hour highly elliptical orbit that spends most of its time over the northern or southern hemisphere, just depending how you design it. That is a day divided by 2. We solve the 24-hour generation problem by having a constellation, which means 2 or more satellites in orbit. In our case, we call them arrays, which are many satellites put together in the same array. And so if your one's overhead for 12 hours, it's also 12 hours overhead on the exactly opposite side of the planet. And if you have 2, 12 hours apart, you have continuous coverage on the ground. We actually plan a constellation of 8 arrays in the northern hemisphere and 8 arrays in the southern hemisphere, so you can have a redundant coverage globally. That's a relatively small number of arrays in orbit compared to the systems that are up there today. Starlink constellation, for example, is about 4,000 elements, and they have plans to get to 40,000. So 16 doesn't seem like very many. Molniya is a relatively unpopulated orbit. There's only about 7 things up there today, so we expect it to be uncrowded and not really have to worry about running into other things.
Virtus Solis is only one of several companies around the world who have plans for space-based solar power. How do you cooperate, or how do you compete with each other?
It's a very nascent industry. There are really only 2 commercial entities declared that they have working on this topic. Space Solar in the UK, which is a spin-off of the Satellite Catapult, which is an aerospace tier 1 in the UK, and then us in the US. There's about a half dozen startups in the US that we're aware of. They're still in stealth, and we don't really know what they're doing, but are probably commercial focused because they are startups. So we know each other. We talk to our industry competitors. We haven't settled on a standard yet, how these things operate. We're still trying to figure out what the best solution is. As an example, we are part of the UK Space Energy Initiative, which was originally set up so that Space Solar could operate. We have meetings, we talk about common issues. One of the bigger things to understand is the regulatory environment, and we think we have a handle on that. Where there's opportunities to cooperate that don't materially affect our business, we do. Things that we can share, those opportunities are certainly there. We're still negotiating and figuring things out, but we expect that this market is probably big enough for all of us. And who has the best solution is still to be determined.
What about Chinese or Indian or Japanese?
Yes, there are government entities that have been studying this for a long time. The Japanese effort has been very minimally funded. They say they're going to do a demonstration on orbit by 2025, but it's going to be very small, tens of watts as opposed to kilowatts or megawatts, which is what power stations need. The Chinese, we really don't know what they're doing. They have declared that they're working on it, but when they're going to demonstrate the first system, we don't know. There's no Indian projects that we're aware of. So it's still very, very nascent. There are a few conferences globally on this topic annually, and it's the same people showing up over and over again. We expect there will be more, but there's not a whole lot of investment in this area because the different agencies and the different businesses aren't convinced yet that it's the right solution. They're obviously spreading their bets and investing in lots of different energy solutions to solve all of our challenges, just like the UK is.
In a way, I guess your competition is the nuclear industry, because what you're doing is providing constant, steady baseload. I think you probably call it firm energy, don't you?
Yep.
And that's what the nuclear industry is offering to do. And I guess your argument against them is that your cost per unit of energy will, in a fairly short period, be a lot cheaper than theirs.
Not only that, but I'd argue the status quo is my competitor. At the Wired conference, the very first question I got was, why don't we just pave the Sahara with solar panels and run a cable to wherever the end users are? That thinking ignores the costs of how that might work. Those of you in the UK might be aware there's a plan to put a solar farm in Morocco and run a 3,800 kilometer cable to the UK to make it work. So that's a $4 billion project just for distribution of energy. It doesn't work all the time either because at night it shuts off, just like every other form of solar. So you could do that, but almost all the net zero solutions that have been proposed increase energy costs, either energy storage costs, which if you know batteries very well, and I've worked professionally in them and so has my co-founder, there's no path to large-scale energy storage. Not today. There's no existing technologies that are going to get us there. It's too complex a product and too dependent on very critical minerals. So those solutions are possible, but they make energy more expensive for everyone. If you look at global use of energy, we in the West, as I said earlier, use about 10 kilowatts on average across all forms of energy. The global average is about 1.8. So compared to what we live with in the US, we'd argue that the whole rest of the world is in energy poverty already. And there's about 750 million people who are at zero. So the true demand is probably much, much higher. In order to satisfy the demand, the energy costs have to be low enough that they're accessible by everyone. The trends that are raising energy costs, number one, the fossil fuels, the easy to dig out of the ground, have already been dug out of the ground. Costs are higher for all fossil fuel producers. And then these alternatives we have need backup. You might know that as renewables have higher and higher penetration, the generation that needs to offset when they're not available, when they're intermittent nature, basically become lower and lower return on investment. So if you have a nuclear power plant that only is operating half the time, its cost of energy goes up because its overhead costs, frankly, mostly capital costs for nuclear, make it worse. Most of the time, most of the markets globally, energy is more expensive at night. It used to be the opposite because demand was lower and those assets were generating during the day and the night, and they were able to provide discounts. Nuclear specifically has a challenge in that we stopped building nuclear reactors in 1982, effectively, at least those of us in the West. And there have been no new construction. So the people who knew how to build them aged out and left the industry. The only nuclear power plant that has been built in the West in the last 40 years is Plant Vogtle, Units 3 and 4 in Georgia. Those two 1.1 gigawatt power plants cost $17 billion apiece and took about 20 years to construct. That is $170 a megawatt hour on average to ratepayers, in addition to the construction costs. So those systems are not economical. Those are, like I said, driving the costs higher. Nuclear is great. I actually am a failed PhD in nuclear engineering. I didn't finish my PhD, but I believed that that technology had a chance to scale, but the regulatory structure hasn't allowed us to build something that is better. There are new nuclear solutions, fluid-fueled reactors, thorium, all those other interesting things, which are totally possible and could solve our energy challenges. But those are complex, and complex solutions don't scale quickly. Personally, I'm almost 53. Maybe got another 20 years left in me, and I don't know that we can get new nuclear scaled to the degree there would need to be in the time I have left.
Well, John, at 53, frankly, you're a spring chicken, and I'm sure you've got much more than 20 years. I certainly hope you have.
I hope so.
This has been a fascinating conversation. Thank you very much for joining us. David and I often talk about the goal of achieving abundance, economic abundance, and a big part of that is energy that's too cheap to meter. And it's very exciting that there are a number of technologies being developed which could get us there, and yours is clearly one of them. So we wish you all the best in successfully developing and deploying it.
Very much appreciate that.
If some of the listeners did want to hurry things along, if they wanted to become involved as a supporter of some of the ideas you've talked about, what should they do?
There are lots of ways. Lobby your government officials for sure, because they need education. There are other ways to get involved. I'd encourage you to contact us directly if you're interested in talking to us about it. My website has an email, info@vertisolus.space. I'm happy to take questions or comments. But as a nascent industry, make your voice heard. There are lots of solutions out there, and picking the right one is probably a challenge for everyone. Educate yourself and have conversations with decision makers. Those are the best ways to make things happen.
That's excellent advice. I look forward to more people supporting this as one of several possible solutions to getting to energy that's clean and too cheap to meter. Thanks very much for your time, John.
You're quite welcome.